Reaction rates. An electric charge triggered by a collision starts this reaction where sodium azide, over here, it's a powder, is converted to nitrogen gas in 0.030 seconds to inflate the airbag with the gaseous nitrogen here for passenger protection. In contrast, when a metal structure rusts, like these nails, the reaction is slow and continues for years. So we have iron reacting with oxygen to form iron oxide or rust. In kinetics, we study the rate at which a chemical reaction occurs. Rate is in general a measurement of change over time. Kinetics measures the change in concentration of reactants and products over time. A chemical reaction involves a change in the arrangements of atoms, which is a change in their chemical bonds. Now, in order for atoms or molecules to react with one another, they have to collide with each other. Once the atoms or molecules collide, there are factors that will affect the rates. 1, the physical state of the reactants, the concentration of the reactants, number 2, the temperature of the reaction, number 3, the presence of a catalyst, or the absence of a catalyst, 4, and finally, 5, the surface area of the contact points. In order to react, molecules must come in contact with each other. If reactants are in different phases, right, solid, liquid, gas, the reaction only takes place at the surfaces where they're in contact. A heterogeneous reaction takes place between reactants in different phases, solid, liquid, gas. The more homogeneous the mixture of reactants over here, the more frequently they will collide and the faster they can react. Because over here, you're only going to react at this surface area right here between these molecules and these molecules. Here, where they're all spread out, you have a greater area where the collisions can occur. As the concentration of reactants increases, so does the likelihood that reactant molecules will collide. The reaction shown here, right down here, is the combustion of methane in the presence of oxygen in a Bunsen burner, creating carbon dioxide and water. So you've got your gas coming in here, you've got air or oxygen coming in through the air hole. They combust, well, you got to put a spark up here first, and then you get the fires here. As more air is mixed with the methane over here, the rate of the combustion reaction increases and the flame gets more blue in color. Recall that blue light has more energy than red light. As the rate of reaction increases, the rate of energy being released also increases, and the more blue the flame. At higher temperatures, reactant molecules have higher average kinetic energies. Molecules with higher kinetic energies move faster. They collide more frequently and with greater energy. As long as the molecules remain stable, increases in temperature leads to increases in reaction rates. Catalysts are substances that speed up reactions by changing the pathway of the reaction. Without changing the reactants or products of a reaction, catalysts influence both the rate of collision and the orientation of reactants, increasing the reaction rate. Basically, they give you a place where the reaction can occur. Catalysts are unchanged by the reactions they facilitate. Platinum-based alloys, very expensive metal, are commonly used catalysts. And again, they provide a place for the 2 reactants or 3 reactants, whatever, to come together and hit each other in the proper orientation so they can react. Reactions with solid reactants will proceed faster as the surface area increases. More surface area allows for more collisions between particles. A steel bar will not ignite if exposed to a flame. In contrast, that same steel, if it's in the shape of a steel wool pad, will ignite and burn very quickly due to the wool's texture, which exposes more iron molecules to oxygen. And here's a great video to watch steel wool burn. In a chemical reaction, bonds are broken and new bonds are formed. Atoms or molecules can only react if they collide with each other. So here we have chlorine plus nitrosyl chloride, and this is before collision, nothing's happening. Then they collide, and they can have a reaction which then forms chlorine gas plus nitrogen oxide. Furthermore, Molecules must collide with the correct orientation and with enough energy to cause bond breakage and formation. Effective molecular collisions are like people meeting in a crowd. To meet someone, you have to move, bump into them, and then shake hands with them. If you don't move, you'll never bump into each other. Orientation is also important. If either of you has their back turned towards the other, you might collide, but you will not meet. Here's fluorine gas, a molecule of fluorine gas, approaching a molecule of nitrogen dioxide. And we're going to do it in 3 different fashions. The first one, they meet with the correct orientation, but not enough kinetic energy. So they strike each other like this, so far so good, but not enough kinetic energy for the reaction to occur. So the fluorine just bounces off this way, and there goes nitrogen dioxide, no reaction. Let's go to the bottom one. This time, they're approaching with correct kinetic energy, but the wrong orientation. So they form like this, but the nitrogen can't reach the fluorine to bond with, and then they just bounce off and go on their way, no reaction. And here, this is just right. They have the right energy, and they have the right orientation. So they form this, an intermediate step, which looks just like the one in part A, but this time there's enough kinetic energy, and the nitrogen will take away the fluorine atom, and one fluorine will go this way, and then you have this new molecule formed over here. Reaction rates can be determined by monitoring the change in concentration of either reactants or products as a function of time. So what do we have here? We have 1 mole of A. 20 seconds later, we have 0.5 mole of A and 0.5 mole of B. And finally, 0.25 mole of A and 0.75 mole of B. In this reaction, the concentration of butyl chloride, and that forms 1 butanol over here, but we're just going to worry about the reactants now, was measured at various times. Now be careful with this chart. The times shown are incremental times. For example, the second 50-second interval here indicates 100 seconds from the initiation of the reaction. See, it has, this is where it starts, then 50 seconds later, then 100 seconds later, then 150 seconds later, then 200 seconds later, etc. And over here, this shows the concentration or molarity over time. The average rate of the reaction over each interval is the change in concentration divided by the change in time. So this rate right here is this delta here. That would be 0.1000 minus 0.0905 divided by the interval 50 seconds, and so on. Reaction rate is like speed, but speed is measured in distance per unit time, and reaction rate is measured in moles per unit time. The square brackets over here, and also over here, they represent the molarity, M, in moles per liter of the species. And molarity is also called molar concentration. The average rate decreases as the reaction proceeds, as hopefully you can see in this oval. As the reaction goes forward, there are fewer collisions between reactant molecules. You have less reactant molecules, therefore less reactions. So let's see. We start at 1.90 times 10 to the minus 4th, and down here we're 0.560 times 10 to the minus 4th. A plot of butyl chloride, concentration there, right, that's what those brackets are, versus time, yields this curve, that green line there. The slope of a line tangent to the curve at any point, and you can see, hopefully you can see that black line, that's tangent to probably this point right here. That is the instantaneous rate at that time. Note that the slope of the curve decreases over time as the reaction rate slows, because the reaction rate is rise over run, or concentration over time. All reactions slow down over time. Right over here where the reaction first started, hopefully you can see how that's a pretty big slope. So that's the instantaneous rate at t equals 0 seconds. Over here, the tangent slope is a lot less. That's your instantaneous rate at 600 seconds. So the rate here is much less than the rate here. Therefore, the best indicator of the rate of reaction is the instantaneous rate near the beginning. At this time, we assume we are looking at the rate of the forward reaction unaffected by the reverse reactions. In this reaction, the ratio of butyl chloride to 1-butanol is 1:1, right? Because there's a 1 in front of each one when you talk about their moles for the reaction. So the rate of disappearance of butyl chloride is the same as the rate of appearance of 1-butanol. And we express that like this: the concentration of both molecules divided by time. And since one is disappearing while the other is appearing, we have a negative sign. Right? This guy's decreasing, so that's why the negative is here, and this molecule is increasing at the same rate.